Okay, so we continue today's lecture. We are on chapter 3 about the ergodic theorems. So if you remember last time, I started with a motivation of this chapter, and we started on this first section, 3.1, which is von Neumann ergodic theorem. So when we were studying this, we needed some structure. We needed to recall like some things from functional analysis, like we have a Hilbert space. And if you remember last time, we also talked about like when you have a closed subset. So when you have a Hilbert space, you have a norm, so you have a topology. So we can talk about closed subspace. And we define the orthogonal of F, which is a subset V in H that are orthogonal. V U equals 0 for all U in H. Okay. You can see, and we gave a basic example, which is the example that we will use, which was the L2 space. So we have mu, we have M, a topological space. We had a mu, a Borel measure. You define L2 mu is the set of functions that are square integrable. So phi such that the integral of phi squared d mu is finite. So this is a Hilbert space, and the inner product is given by just L2 phi c d mu. Okay, and if we take F, if you remember, if we choose F as a space of constant functions, remember, we have also defined the orthogonal projection. So PF V was V orthogonal, such that you write, V. PFV is defined such that you can write V as PFV plus V orthogonal, where here you have this guy is in F, and this guy is in F orthogonal, as this total space is written as a direct product of F and of F orthogonal. Okay. Okay. Yeah. Think of the usual projection. So I'm writing something wrong here. And in this example, PF. So in this example, we have seen that P F C is just the integral of C d mu. You have a function that is integrable. If you want to see what is the the projection of this function to the space of constant function, is just the mean or the average or the the space average of this function. Okay. So before I state the theorem of von Neumann ergodic theorem, I want to tell you about adjoint operators and isometry. Okay. So recall adjoint operator. So if you have U, so let U from H to H be linear and continuous. The adjoint operator of U is U star, that is from H to H, and this is defined by U V is U star V. Okay, yeah. So if you haven't seen this, if you are familiar with matrices, think of this just being as like, in the case of U being a matrix acting on R2 or Rn, a square matrix. So this is just the transpose of the matrix. Okay. So it has this definition in infinite space. So this is the definition, and we say that U is an isometry if the matrix is preserved by U. So if UV equals UV for all UV in H. So yeah. As an example of isometry and linear operator that we will be using is the Koopman operator. So example. Koopman operator. This is another operator that is very much used in dynamical system, like also the transfer operator that we defined in the previous lectures. So if you have F, that is defined from H to H, oh, I'm talking about the dynamical system here. So you have here your system, and U, so from L to, oh, sorry, I used something wrong here. So I should not use little l, I should use big L because this is for the sequences, okay? So this is L2. Okay, this is capital L, so the notation is important. Little l is something else. Okay, is the space of sequences where the sum of the square is summable. Like the sum of the square is finite. So this is L2, mu. So L2 is H, is the Banach space. So U of phi equals phi composed with F. So this is the Koopman operator. Unlike the transfer operator or the Perron-Frobenius operator. I think I did not use transfer operator, this language. I don't know. Like if you remember, we had this operator PF, which was the Perron-Frobenius operator. And this was used to find densities of invariant measures for a dynamical system. Here, this is another operator which is used to find invariant functions. So, definition. So, if you have a function phi from M to R measurable is F invariant, if phi composed with F equals phi. So this is the definition of an invariant function. And we will see later that in general, in most systems that we are considering, invariant functions are just the constant function. Okay? Because you can think of being invariant as, you know, for instance, if you have a dense orbit, if your dynamical system has a dense orbit, if you have an invariant function that is continuous, it has to be constant because the value has to be the same everywhere on your space. It has to be constant. And we will see also in the next chapter that because, let me put this as a remark, is that if phi is continuous and F has a dense orbit, dense orbit meaning, so there exists P in M such that F and P is the whole space, the closure of this. Okay, like this orbit is going everywhere in the space, so this is the closure topologically. So phi F invariant imply that phi equals constant. Okay, but in the next chapter we will see. Before that, so this property here, having a dense orbit, is something that, you know, many people, I would not say physicists, but there are some people who really, you know, think of this as being ergodic. Like you have a point that goes everywhere. Because if you think of ergodicity, what is ergodicity? Is that, you know, you cannot decompose your space into two subsets that are invariant in a measure theoretic sense. A dense orbit, you know, will go to everywhere. We go to all the space. So you might think that dense orbit is something related to ergodicity. But if you want to talk about, you know, if you want to talk about it rigorously, they are not the same. Okay, they are not really the same. But with this property, with this kind of property, later we will see that if the system, if you replace this by ergodic, you still have this property. Okay, we will see that later. Having a dense orbit doesn't mean ergodicity. Yeah, in general, you cannot compare them. Okay, you cannot compare them. Those two properties are different, but we will see that later. So yeah, so Koopman operator is used to find invariant functions. Okay, and a remark is that the Koopman operator is an isometry. Koopman operator is an isometry. Yeah, under you have under invariance. Okay, so I'm supporting that under mu F invariant. Okay, if mu is F invariant, so the Koopman operator is an isometry. So you can see how to, it is easy because you can just take u phi c. This is the integral of phi composed with f and c composed with f d mu. So if you want, you can write it as the integral of phi c composed with f d mu. And we have seen that this is the integral of phi times c df star mu. Yeah, this we have seen how to get this. Do it by, the step that we are used to. And this being invariant, it tells you that this is f star mu is mu, so this is phi c. So this is an isometry, an example of isometry. Yeah, before I state the theorem, the von Neumann ergodic theorem, there's just one last definition. So the von Neumann theorem is for general operator, not only Koopman operator. So we start, let u from h to h be linear and continuous. So we write the invariant set of u is I u the set of v in H such that u v equals v. Okay. Yep. So this is the set of invariant V's of u, or you can write it as the kernel of u minus identity. Okay, because you can put this equals 0 and yeah. So this is the theorem. Von Neumann ergodic theorem. It tells you that. So all the theorems we will see here is about space average going to time average going to space average. So let u from H be an isometry, and then you have the following, that the limit when n goes to infinity of 1 over n, the sum j equals 0 n minus 1 u j v is just p I u of v. So this is the projection to this subspace. So this is a subspace, okay? You can check that. It is linear, 0 is inside, and all the properties. And this is for all v. For all v in H, okay? As I said last week, that the conclusion of this theorem is strong because you have strong assumptions. Like the fact that you have these conversions for every H is something very strong, because you have isometry and also you have a structure on your space being a Hilbert space. Okay? And this quantity also, we can think of it as a space average. Okay? As you can see in the example of L2, the projection to this invariant function is like the projection to the constant function is like the integral, which is a space average. Okay. Okay, let's prove this. So we'll prove it and do some applications and then go. So first of all, this you have it to be true when V is in IU. So it is obvious that 1 over n, the sum j equals 0, n minus 1 of u j v equals v for all v in IU, right? So if you are in IU, this is just v, so you sum in the same quantities, so it is n times that, divide by n, you get v here. And this, for v in here, you have p IU v equals v. So this is p IU v, so you don't need even to go to the limit, you have this at finite step. You have this equality at just finite step. Okay, now we need to check, so need to check for v not in IU, or let's say for v in IU orthogonal, because it is complementary to IU. All right, to do this, let's try to understand what is IU orthogonal, the orthogonal of this subspace. So need to know IU orthogonal. Okay. So there's a candidate for this, because as you may be used to this stuff that, when you want to write a space, you have a linear operator on that. In general, you can write it as a kernel plus the image of this operator. So because remember that IU is just the kernel of U minus identity. Okay. So our claim is that IU orthogonal is the closure of the image of U minus identity. Closure. Okay. So when I say closure here is with respect to the topology that is given by the Hilbert structure, by the norm, by the metric you have here. Okay. Let's write this space as, just for notation, L of U is the image of U minus identity. So if you pick a vector point here, so let W be in LU closure. By definition of the closure, we have a subsequent that exists WN in H in UN in H such that WN, which is in the image, so U of UN minus UN is converging to W. So this is just this is small u. Okay, this is just the definition of the closure. If you want the closure, you have a sequence that is converging to the point. Okay, and yeah, in the sequence being in this space, you can write it, you have your un, okay? So now let us see. So we want to prove that this vector here is orthogonal, is in the orthogonal of IU. So to do that, we pick V in IU, and we want to know what is VW. Okay, we want to prove that this is 0. Okay, for every W, for every V. Sorry. Now let's see if we just check it for the Wn, and then we go to the limit. So VWN is just VUN, UN minus UN. Sorry. So this is VUN minus VUN, okay? So just use linearity of the integral. Here we are going to use a property of, U being an isometry and V belonging to. So first of all, here you can write it as U star VUN minus. Okay? So here U being isometry, so this is a point where we use isometry, and the fact that V is in IU, so U V equals V, this also implies that U star V equals V. Okay? This is just from, you can check it from that definition of the definition of isometry. So you come back here to see that VWN is 0. Okay, because this is V, so you have this is 0, and this you go to the limit, so this implies that VW equals 0, and V was arbitrary here, so V arbitrary imply that this W is in IU orthogonal. Okay. So now we want to prove the reverse. So what did we do? We proved that LU, the closure of the image, is a subset of IU orthogonal. Okay? So this proves this. So let me rewrite it here. LU closure is a subset of IU orthogonal. But see that when you go to the orthogonal to these spaces, so I will write it and explain why it is true. So this is equivalent to say that IU is a subset of LU closure orthogonal. This is just using these basic properties of the orthogonal, because if one set is, the way to think about this is just the complements of a set. This is just, think of it as being a complement of the set. When you take complement to the complement, you have to invert this inclusion sign. Okay. Sorry. Yeah. So if a subspace is inside the orthogonal of a subspace, that means that this space is inside the orthogonal of this one. And the orthogonal by its definition is a closed set. Here, this you can write it as L of U orthogonal. This itself is a closed set, so you don't need to take closure. Okay? So now, so this is what we prove. So we want to prove the reverse. So we want to prove that, so we are left to prove, I mean, for the claim to be true, this guy here is a subset of IU. So we pick V in LU orthogonal. What does this mean? This means that V U minus U, so this is the image, this guy equals 0 for all U in H. Okay, because this is the image, this is LU. This is arbitrary point in LU, okay? Okay, so this in particular, it means that V U of V equals V U for every U in H, or yeah, I've been rewriting some nonsense here. U equals VU for every U. And if you have this, that means that these 2 points are the same. These 2 vectors are the same. Okay, this is true for every U, so it implies in particular that U star V equals V, and U being an isometry, so I should be consistent with the notation. These are small. And is under isometry is equivalent to U of V equals V. So V is in IU. Okay. Yeah. So I think I spent too much time on this. Yeah. So this proved the other inclusion. So this implies that V is in IU. So we are done. We are done with this claim that IU orthogonal is the image. So if you take a point in the image, so let V be any point. So back to the proof of von Neumann. We've just finished this claim. If you take V as a point in the image, so let me write it like this, equals to U minus U is a point in the image of U minus identity. Now you want to take the time average of this guy. So 1 over n, the sum j equals 0 to n minus 1 of U j of V. This is 1 over n. Yeah, so you will have uj plus 1, u minus u, j, u. And if you write this, what you get, because you will see cancellations, so you will have this term which will cancel the one that is coming at n plus 1. So what you would have is the difference between the first term u and u minus u. Okay? And this guy is going to 0 because u is an isometry. This is an isometry, so this is uniformly bounded. The norm of this is just the norm of u, okay? And the norm of u is independent of n, so this goes to 0 as n goes to infinity. And 0 is just the projection, because if you are in the orthogonal, is P I V I U of V. Okay. Yeah, this I did it for a vector in the image. For a vector in the closure, you just do approximation. Okay, I do it here for the image in the closure. You have approximation. So yeah, this proves the von Neumann theorem. Okay. Let's see an application of this theorem to some dynamical system. Okay. The application can be obtained in this corollary. So phi is in L2 mu, and phi orthogonal, as we've seen the other time, is just the integral of phi d mu. So this is the orthogonal, the projection. No, what did I say? So I am saying the projection. Okay, sorry. This is what I want to say. So and F is the space of F invariant functions. So F invariant, I just mean the space of functions that you compose with F equals phi. Then 1 over n is converging L2, okay, to P F of phi. So here the proof is simple. It's just von Neumann for the Koopman operator. Okay. Proof. U equals UF is Koopman operator. Yeah, there is also a version of this theorem for flows, okay, for continuous time dynamical system. So remark. So von Neumann for flows so for that you have a family of operators ut, that is ut from h to h. So the theorem, it tells you that 1 over t, the integral from 0 to t of ut v dt is converging to p of v, where here p is so the invariant set of ut. The invariant set of ut being I ut is the kernel of identity minus ut. Yeah. Yeah. So this was an Ergódica theorem which doesn't give any type of pointwise convergence, as you can see here. It gives the convergence of the function because this is an L2 convergence. Okay. It doesn't give the convergence on like pointwise, like as I was explaining at the beginning of this chapter, that if you put here a point x, what do you get? Okay. So now this next section is about, you know, trying to get pointwise convergence. So 3.2 is Birkoff Ergódica theorem. So so it's about, you know, instead of having this convergence on L2, have it for every point x here, you know, the convergence to something for a phi being an observable. Okay. So I will start with an example which just tells you that in general you don't hope to get, you know, convergence to the same limit for different x if you put here different point, even for this simple decimal expansion 10x mod 1. 10x mod 1, okay? So this is just the decimal expansion, okay? So this tells you that like fn, so if you pick x in 0, 1, fnx, the leading digit of fnx gives the nth integer in the decimal expansion. What I mean is, if you take x, you can write it as point x1, x2, x3, and so on, xn, and so on. So fn of x is point xn, xn plus 1, and so on. So this is called the decimal expansion. So let's consider this point here, x, which is, so I take 1 and 0 twice, and then 1 4 times. So this is 1, 2 to the power 0, and this is 0, 2 to the power 1, and I have 1, 2 to the power 2, and then 0 8 times, 2 cube, 1, 2, 4, and so on. So this is just alternating. And there's something also interesting in this dynamical system that, you know, if the point is periodic, that means that you have a rational that gives a rational number, okay? Like if the number you start with is rational, you will see a block that is repeating here. Okay, if the number was rational, you will see a block that is repeating. And if it is irrational, you cannot have that. And for instance, you know, you could see if you have an irrational number, you can approximate it by a rational one by just, you know, if this guy was rational, if I pick another number, x prime, so that they have the first n digit, and I just repeat this guy here, I will have a rational number that approximates the original that you started with. This is a guy that is not rational. You don't see any repeating block. Okay, this is irrational in 0, 1. And consider this set E to be 0, 1 over 10. And what is this set? This set is the set of numbers in 0, 1 such that the leading digit is 0. These guys, their first digit is always 0. So E is a set of points in 0, 1, or numbers, such that the first digit in the decimal approximation is 0. The first digit in decimal expansion is 0. Okay? So if you take here, there is something interesting in this. So if you look at this sum, the sum of j equals 0 n minus 1 of the indicator function of E composed with, so our observable that we have there is the indicator function of this set E of f j x. F is 10x mod 1. So here you will observe that you have two different sequences of numbers. Okay, so you can see that here the first one is not inside. So for j equals 0, this is 0, and the second one is inside, and it stays. So it is, what you get is 2, 2, 1 plus 2 cube plus 2k. I will say 2k minus 1. This is for n equals 2k minus 1 for n equals 2k minus 1, and k is even here. K is even, okay? Okay? And on the other side, when k is odd, the other sequence you have will be, you will stop at 2k minus 2. So 2, 1, 2 third plus 2k minus 2 over 2k minus 1. So for the same, and k is odd. Okay, and this you can see that this is 2/3 and this is 1/3. So depending on n, you have two limits of the time average, okay? So if n is of this form and k is even, you have 2/3, and if n is like this and k odd, you have this. So this is just telling you that there are points for which you don't have convergence. You don't have convergence point-wise of the time average. So as I was saying here we have convergence of the functions. And in this chapter, we are interested in convergence point-wise. In this section, convergence point-wise. Already this example is telling you that there are points where you don't have convergence point-wise. So we are not looking for convergence point-wise, but point-wise in a measure theoretic sense, like there is a full measure set where you have this convergence. Because, okay, this is just one point. How about what is the measure of this set of points where you don't have this convergence? So this chapter, this section will tell us that under some condition on the measure, that set of points where you don't have convergence has zero measure. Okay. So before I state the theorem, I have to define what subadditive mean. So the takeaway from that example is, let me write it here. Is that there are points, so I should write it like this, where space average, time average doesn't converge to space average. Average does not converge to space average. And the aim of this section is to prove that under some, so if mu is F invariant, there exists a full measure set. There exists a full measure set, full mu measure set such that you have this convergence. So we have convergence. Okay, this is what we will see in this chapter. And this full measure set, in general, it will depend on the potential you choose, on the observable. Okay, so usually I call this function observable, okay? This phi that you plug into the is an observable. And we will see that if we put some structure again on our metric space, we will have a full measure set that works for all functions. So definition. A sequence of functions C n from M to R is subadditive for F F is a dynamical system, okay? If you have phi of M plus N is less or equals to phi of M plus phi of N composed with Fn. Yeah, so this is a definition, an example of subadditive functions. You can take, phi, your space here, M here is a space of square matrices. So M is a space of squared matrices. Okay, I'm talking about real integers, okay, real entries, okay, and F being identity of M, and if you take phi n of A of a matrix is the log of AN. So this sequence will be subadditive because of, the subadditivity of you have that phi n plus m of a equals log of a n plus m, which is less than log of a n plus log of a m. Okay, so, and this is phi n plus phi, okay, n plus, yeah, I use something different, m plus phi n, because f is identity, okay? F is identity. Also, another sequence that is subadditive is the time average, okay? So for today's lecture, I will just hop to, I will not prove the whole ergodic theorem, but I will give more application, go to, toward the happen of exponents of a system using these theorems. So this is one example also. Phi n, the time average, which is defined as phi n is the sum I equals 0 n minus 1 of phi I of x. This sequence here is subadditive. It's subadditive with respect to f. F is any dynamical system. Subadditive. Yes, so let me state the Birkoff since I have defined here subadditivity, so it just makes sense to state this theorem, which is Kingman theorem. So it is a subadditive ergodic theorem. So what does it say? It says that f from m to m is measurable, okay? Mu is f invariant. If you have a sequence of functions Cn subadditive, and measurable, so anything I'm using here with, so there is another property that the first one is integrable, which is the maximum between 0 and C1. This guy is in L1 mu. Okay, because you just need this condition on the first one, because if you have invariance and subadditivity, you can conclude that the others are also integrable. So the theorem, the subadditive ergodic theorem, then phi n over n is converging mu almost everywhere. So we have a pointwise convergence, almost everywhere convergence to phi, that is from m to minus infinity plus infinity. And this function, the limit is f invariant, and C is f invariant. And what you have is that, moreover, the integral of phi d mu is just the limit of 1 over n, the integral of phi d mu as n goes to infinity. So this theorem, so we will prove this probably next lecture. The proof probably will take the whole lecture.
Inside the integral?
Inside, it doesn't really matter here. Oh.
Inside?
What did I write here? Yes. Sorry, yes. Yes. Yeah. Yes. So as I just said, this theorem we will prove it next lecture. For today's lecture, I will try to go to applications of this theorem of Kingman theorem. The proof is quite long and very abstract, so I don't think I have the energy to do it today. So we will do the proof on Wednesday of this. So an application of this is the Birkoff Birkoff theorem. So it tells you that if you have f, so if you're following the book, this is theorem 3.2.1 in the book, okay? F from M to M and mu F invariant. If you take E is a Borel set with positive measure. Remember the mean sojourn here equals the limit when n goes to infinity of 1 over n, the cardinality of j 0, j n minus 1. So in the previous chapters, we have seen that this limit exists. We can, under invariance, sorry, we have seen that we did not see that this limit exists. We have seen that point is returned infinitely many times. And we had seen the integrability of the return times. Okay, the return times, the first return time is integrable. That's what we have seen. So this Birkoff theorem tells you that this limit exists for mu almost every x. Okay, unlike this is the point where this limit doesn't exist in this example, because this point is in a set of 0 measure. So this is key here. Mu almost every x is important. And we know more is, the integral d mu x, that is the measure of E. So this is the Birkoff theorem that just requires invariance, okay? That just requires invariance. This is the only condition we have here. So already invariance tells you that you have these time averages that are converging to a function that is integrable, okay? Later on, we will see that this is constant. That's what we will see, that this function is constant and is a space average when we put mu is ergodic. When you have invariance and ergodic, you have that this limit here will be constant for mu almost every. Okay. Yeah, the proof of this is just an application of Kingman theorem. So yeah, so the proof is just application of this. So apply Kingman for, so this is called Kingman theorem or subadditive ergodic theorem. This is Birkoff theorem, and some people, when you add ergodic here and you have this guy is constant, some people call that one also the Birkoff ergodic theorem. So at this stage we just have Birkoff theorem. So for this sequence, for phi n to be the sum of the indicator of E, goes with fi, I equals 0, n minus 1. Yeah, and Kingman tells you that this limit exists. So this guy will be tau xe, and that the integral, you can see that the integral of tau ex dmi x is the limit when n goes to infinity of 1 over n, the sum of the integral of the indicator function of E composed with f j d mu x x, and by invariance you can see that this f star mu equals mu, so this is the limit when n goes to infinity of 1 over n of, if you want, the indicator function of E d mu, and this is mu of E, and you average, so okay. So that is easy application. So again, don't be, this is something important you should keep in mind when talking about this course about ergodic theory, is this is important. And when you have this convergence for every point, this is a chapter that we will study. Essentially, when you have the time average is converging for every point, so that is called unique ergodicity. So that is a chapter on its own that we will see. But in general, all these convergences are with respect to a measure. And remember this example here. There are many others. Okay, there are many others. So there will be a chapter dedicated to, this these systems where you have convergence for every point, regardless of a measure. And those systems, they have some strong property that there exists a unique invariant measure, and that measure is ergodic. And that's why they are called unique ergodic systems. Yeah, there is the version of this theorem, because I do it for the indicator function here for E. So there is a general theorem for general observable theorem, Birkoff for general observable. So you take a dynamical system, and mu is F invariant, and phi is an integrable, is an L1 mu. Then you have phi tilde x, which is limit when n goes to infinity of 1 over n, j equals 0, n minus 1, phi composed with fjx exists. So this function exists for mu almost every x. So every x. And the integral of phi tilde d mu equal the integral of the function you started with. Yeah. So I will not do the proof, it's the same, okay? It uses the same. You just do Kingman. So I wanted to talk about Yapon of exponents, but I don't think. Okay. Anyway, so this is a very important theorem in dynamical system. That if you see, it just needs invariance. That's a condition. It is very much used in dynamics because, for instance, we will see in next lecture how to define the Yapon of exponents using this theorem. And the Yapon of exponents is a quantity that measures sometimes, if you want to say the chaoticity of this system, or if you want to say the hyperbolicity of this system. Okay, we will see how to define Yapon of exponents using this theorem. Yeah. Before I close, let me just tell you that, see that here, the points where you have convergence, it depends on the function you started with. Okay? So remark is that set given phi, so the above this theorem, so Birkoff says that given phi that exists G phi in B, a Borel set says that mu of G phi equals 1, and in G phi you have convergence. So G phi is just the set of x in E such that this limit exists, that phi tilde of x exists. So now there is, if you put some more structure on your space, like if you have M is a compact metric space, and you consider the continuous function, you can have one set that works for all by just using the fact that the C0, the continuous function is, the space of continuous function is separable. It has a countable dense subset. So theorem is that if M, so let M be compact metric space, and then F, you have M, and mu is F invariant. So there exists a full measure set mu, a full measure set G, mu measure, okay? A full mu measure set G such that you have 1 over n, the sum of j equals 0, n minus 1, phi composed with fjx. This guy is converging to phi tilde of x for all phi that is continuous in C0M, and for all x in G. Okay. So the compact metric space is just to have separable, and then you have a countable dense subset, and you can do yes, the idea of proving this is just to choose a countable dense set, and for each point in that set, for each function in that set, you have your G and take the intersection of the G. And the intersection will have full measure because of measure theory, the theorems you know from measure theory that if you have a sequence, a countable set of a countable collection of sets with full measure, the intersection will also have full measure. And if you take an arbitrary function, you use the fact that the function is close to a function on that dense countable set. And then, yeah, we can do this. We can start next lecture with this proof. It's proving this, which is not difficult. The idea is just using the approximation and putting lim sup and lim inf because we don't know yet where this limit exists. Yeah, so I would say this is very important for what is coming next. And the key is just using invariant. We haven't proved it yet because we just derived it from Kingman theorem. So the main proof is here, is this. This is the theorem that requires a proof, which is quite long proof. We will do it next lecture. So we will do the proof of this and go to applications like Lyapunov exponents, and yeah, we will do the application using Lyapunov exponents also, like the definition of Lyapunov exponents using this theorem. And in general, in dynamical system, Lyapunov exponent is very important because it is a way to give, to split your space, to have a splitting of your space. Let's say in general, when you wanna study a dynamical system, it always makes sense to reduce the dimension, like go to one dimensional, like, or let's say to linearize your dynamical system, like find subspaces that are invariant. Like if you have a matrix, for instance, to understand the dynamical system of a matrix, what you do, you find the eigenspaces. And in each eigenspace, you know what the dynamics is doing is just, expanding or contracting by the eigenvector. In general dynamical system, these eigenspaces, you get them via, the definition of Lyapunov exponents and what is known as the isolated splitting. The splitting, but that splitting is based on this theorem. So you need to define what is a Lyapunov exponents using this theorem, and from the Lyapunov exponents, you can have like these eigenspaces in a measure theoretic sense, because everything here will be respect to a measure. Respect to a measure. So if you give me a matrix, I have the splitting everywhere on the space I have, because the matrix, I know what it is. But if you give me a general dynamical system, I don't have this notion of eigenvalues everywhere, but I have it almost everywhere. So almost everywhere I have a notion of eigenspace and eigenvector. So and eigenvalue. Eigenvalue is a generalization. Lyapunov exponent is a kind of a generalization of eigenvalue using this theorem. So this is very important as it goes from it helps us to make a step from matrices to nonlinear system. Like we have matrices, we have eigenspaces, we have eigenvalues. We can use this to define a notion of eigenvalues, which is the Lyapunov exponent, and notion of eigenspace, which we will not do in this course. That is something else, which is isolated splitting. But that is also, if you want to do dynamics, so that is something you should know in the future. Yeah, just so that next lecture we will finish the proof of Kingman. We prove the proof of this Kingman and go to Lyapunov exponents. Okay, so I will stop here for today.